Professor Zhang, you have the floor.
Oh, great. Hello, everyone. Can you hear me?
Yes, we do.
Oh, great. Good afternoon. I think it's the afternoon time in Japan. Right now, I'm at MIT, so I'm presenting from Cambridge, Massachusetts, US. I really appreciate to have this opportunity to present my result based on the tracks on CR-39 from the SPAWAR co-dep experiment. And feel free to ask questions and also leave your question in the chat. So I'm presenting from both two of the team from both MIT and also Global Energy Corp. And I'm also new to the ICCF, and my background is mostly material science and electrochemistry. Hopefully, we can open the discussion for my initial result on this topic. For a brief introduction, Palm, as our collaborator, and her colleagues already reported great tracks from the PDD alloy co-deposition experiment earlier in the past 2 decades. And right now, we consider those are very important experiment and also very solid findings. That's why we think it will be a great opportunity to take this knowledge and continue them and potentially develop them into the low energy, no energy nuclear reaction lab rats. So our big motivation is to try out those experiments in our lab at MIT and to see what is a promising result we will have and to develop for the next future work. So to have a quick recap for the electrodeposition process, usually for the electrochemical cell, we will have an anode, a cathode, and also an electrolyte between them. So once we apply those voltage or current on these two electrodes, we will have those ions start to move between two electrodes, and then we make those ions onto the become the metal or alloy solid and deposit on the electrode surface. So this process we call electrochemical deposition. And in the reported paper developed by Palm's team, so in this setup, we will convert the electrochemical cell more into the way we want. So you will see these two parallel in the horizontal way. This electrode cathode collect those deposition, the PDD deposition on the cathode surface. And we also have the CR-39 directly contact with those cathode for tracking particle during the electrodeposition. And this CR-39 is a very popular commercial detector we can use directly in our developed system. And the most advantage of this material is it is very easy to operate and also cheap to make, and also it is possible to scale up in large scale, because later on when we want to develop larger reactors, we will need larger detectors. So those solid passive radiation detectors will be the main material we'll use as detector in our following slides. So once we have energetic particle generated during the co-dep process, we will have those particles deposited on the surface of a CR-39 and create those paths of ionization and also the environment around it. So the bond break in the polymer, as you can see here, and then those radius and defects start to form around this path. And eventually, after the co-deposition, we will take this CR-39 out of the reactor and start the etching process. So the etching can help us to kind of freeze and permanently store those track formation after the whole process. So this is a process we consider we'll want to use for also in the development at MIT. So what we can see from the etched samples are on this screen on the right side. So since the detector is directly contact the cathode, so that helps to catch more particle density on the relatively small surface area. And the photo A is focused on the surface of CR-39, and photo B is the overlap of two images at a different confocal length. So you can see different lengths of these images can tell us different information of the dimension, the depth, and the angle of those particle tracks. So now we will have this developed methodology of how can we use CR-39 to track those particles and study this energetic particle generation, not only during the reaction, but also even we can store those samples later for the reaction, and possibly we can have in situ real-time measurement as well. So our target is to reproduce the palms and also the pioneers' result in our own experiment setup at MIT, and we continue to study the operational protocols, not only the electro deposition, but also including imaging capturing, data analysis, and probably scale up for different advanced characterization. For example, real-time neutral measurement, and possibly with NMR real-time in situ measurement as well. And our experiment setup looks like this on the right side. So we adapt this conventional cell and modify them into the size and the dimension as we need. So we have anode as a PT material. We have a cathode using the gold coated on the mylar. And we will have palladium chloride and lithium chloride in deuterium heavy water as our electrolyte. And here is a demonstration for 20 milliliter electrolyte. And to give more information about the cathode structure, so we have gold spattered as a cold method to plate on the top of the mylar. So the mylar is 50 micron. So this mylar not only provide the mechanical support for the very thin gold layer, usually only 1 to 2 micron, and also it provide a way to block the low energy particles. So based on what thickness of the mylar we use, we can block a different level of the energy range of the particles. And here the CR-39 is on the other side of mylar, but still closely contact this layer of the cathode. And here the demonstration we use CR-39 from a supplier called Landor. And this is the piece of mylar already have the gold spattered on that. Very soft and also it is flexible. The alloy co-deposition materials, so after electrode deposition, we took everything out. And here I already separate each layer. So you can see this is a piece of the CR-39. This is a mylar, but I also separated the deposited layer. So you can see the yellow color is from gold, but the gold already beneath this PDD layer, so that's why you cannot directly see the metal layer on the mylar. So this is, we already use XRD to confirm this is PDD alloy. And then we take this mylar, this CR-39 piece to etching, and I will show you how those tracks looks like. So the first one I'm showing is the electro deposition, but without deposition on the detector area. So this detector area has been covered by the other material to prevent the deposition. So you can see there's no deposition on the surface on the top of the electrode, and then there's no tracks on the CR-39. So on the contrary, we also observed that energetic particle tracks after the etching of this piece of CR-39, we observed different shape, different dimension, and different morphology of those particles, as you can see here. So it could potentially become like two particles or multiple particles layered tracks together, single particles, triple particles, and also different connection between particles or different development or different angle of the energetic particle damage the bonds. So those are very interesting and also very new to us when we start this trials in the lab at MIT. So we also tried different materials and conditions to see whether this finding is consistent through different electrochemistry cells. So the first one we want to show is we also use this Landor CR-39 to test with our alpha source, which is AM241. So you can see on the right side, I use a material to cover the half of the CR-39, which prevents the energetical particle to make tracks. So which is on the right side. This is the area of covered area. And if we have a look at of different distance of those CR-39, if this image on the left showing it is far from the alpha source, on the right side is very close to the alpha source, which also support the idea of like using CR-39 as a very efficient energetic particle detector. And then we also test out different suppliers of the CR-39. So here is a very cheap, simple ones, because we all know CR-39 can be used as like glasses lens. So this we just buy from like market, like commercial market. We cut them into shapes. We did this coat deposition. You can see this coat deposition layer. And then after etching, we can even use eyes to see this 2.5 by 2.5 centimeter. We already see those particle tracks. So if we use microscope, you can see those particle tracks are very clear. So although like they have like gas bubbles, those are due to the manufacturing of this CR-39 because it's cheap. So it didn't do a very good degassing during the manufacturing, but we can still see the energetic particle make those tracks very clear and outstanding from the background, those ones. So we can see now like CR-39 detection efficiency is nearly almost like 100% for charged energetic particles. And also it can catch a wide range of the particle energy range. And also CR-39 seems like from different supplies also show well function during the experiments. In addition, we have a collaboration with Texas Tech University in the US, and they have the spin-out company called Blank State Technology. They also share their sample with us as a CR-39 piece. So we can see this type of CR-39 in the same setup of the electrode deposition, coat deposition experiment. We also catch like different size of range of the particles. And interestingly, we can see that in this type of CR-39, we kind of like observe smaller size of the particle, like particle tracks, but we receive higher density of those tracks. So we also notice in the community there discussion about whether those tracks are directly caused by the chemical or electrochemical environment, because those CR-39 were immersed in the electrolyte and under this electric field. So I designed this device that can help to get the CR-39 piece out of the whole environment. So it will we have this hole to expose the gold layer to the electrolyte, and this CR-39 is outside the box. And then we detect that this gold layer, it can be really functional as a cathode material as well. And by doing this, we isolate the detector from the chemical and also electrochemical environment. And at the same time, we also separate that from the current. So we use this to repeat the similar condition for the coat deposition. And similarly, we see that on this CR-39, we still can observe the particle tracks, which proves that it is the particle tracks is not due to the chemical or electrochemical environment or the current or electrical field, but it is true due to the energetic particle generation during the co-dep reaction. So I have this quick conclusion is like we observe tracks from Palm's co-dep experiment protocols. We modified according to our experimental target at MIT, and we still consider this is very suitable for the low energy nuclear reaction lab rat, and we will continue to develop that. So we already observed triple traps, which has been seen as I showed in the previous slides. And those triple tracks are due to the energetic neutrons. Those neutrons are energy are higher than 10 MeVs. So we also observe tracks on CR-39 from different suppliers, and that means like it doesn't matter which CR-39. We also we should be able to see different type of tracks on those detectors. And those tracks also observe on the CR-39 even when the detector outside the electrochemical cell, which further prove that those tracks are due to those particles generated during the reaction. So we have future works very interesting and parallel developed at the MIT and both at with the collaborators. We plan to replicate more experiments in our lab and to see to hope to confirm the consistency and the reproducible with our own setup. And right now we're developing the quantitative image analysis methodology with a large data size measurement. And in the summer, we plan to map those different conditions for particle generation, including different current, voltage, temperature, and the concentration of the electrolyte. And we plan to increase the neutron emission rate in the relatively small size of the electrochemical reactors, as you can see in this photo. So this purpose is in order to help to other advanced characterization measurement. For example, real-time neutron measurement. As you can see here, we have 2 neutron detectors. So beyond my work, we also have our team present at this ICCF as well. So please welcome to check their talks and also talking to our collaborators and colleagues. If you have questions, I'm happy to answer. And I really thank my advisor, Peter, my also co-advisor, Yip-Ming Chang, in this project, my colleagues, Sadie, Florian, and Matt at MIT, and also our best collaborators, Pam and Larry, always give our continued support and discussion as time as we need. And also thank my sponsor, Energy Initiative and ExxonMobil. Happy to take any question. Thank you.
So thank you very much. There are some questions, please. Give your name and your question.
Dr. Zhang, can you hear me?
Yes.
Hi, it's Steve Krivet, New Energy Times. Thank you for your presentation. I have a suggestion for you to consider. Maybe it's far out there, but I'll throw it out there anyway.
Okay.
I know that spectroscopists do not like to put messy samples into their devices, but you have a lot of resources at MIT.
Right.
Possible you might find some interesting things if you look for isotopes, shifts, and unusual abundances. So just to want to throw that idea out there to you.
Yeah, thank you very much. Actually, because the time like for this time limit, I couldn't share more information. But actually, we already have a couple of images from SEM, XRD, and also X-ray, like 3D construction X-ray. So we expect to share that later when we have like a more complete picture of our data. Right now, though, you're perfect, right? We have a good template and a platform to study such topic at MIT. But I'm also new to this field, and also people are trying, people have more interest in now. We trying to increase these activities at MIT and trying to explore more different measurement or characterization method for this topic. Thank you.
Hi, Dr. Zhang, Bob Grenier, Martin Fleischmann Memorial Project. Great work, innovative changes to the experiment. Could I ask you, have you tried moderated indium activation or moderated boron-10 tubes to actually detect the neutrons directly, preferably the indium activation with the 54-minute half-life?
That is on the plan. So right now, in this setup, as you can see, that is I'm mostly focused on electrochemistry methodology. I show one comparison with the alpha source. So I think your suggestion is really good. Like as soon as I have the access to the material you suggest, we also expect to have that as making those tracks and compare.
Dr. Zhang, that's great to hear because it's been a long time complaint of this experiment that they may not be real neutrons. So to have indium activation proof would be very, very important.
Please send me email. I shared on my last slides. I can share it again. Please send me email. We are actively looking for collaborators and sponsorship for our research as we want to continue. As you also noticed that those funding cut at the US is not very friendly to our current research. So any information collaboration will very welcome. Please send me email. Thank you.
Thank you, Dr. Zhang.
Yeah.
Maurizio Maggiore, please.
Hello. Yes, I saw that you took the care of doing an experiment isolating the CR-39. I wonder, because I had contacts with a project that presented in previous ICCF and some experiment of co-deposition, and they had a doubt, I quote from what they told me, that the pits in the CR-39 surface could be caused by hydrogen-oxygen recombination reactions. I'm just wondering whether you had the same doubt, you talked to them, or someone else, let's say, signaled this to you. Why did you do it? And happy that you confirmed that that's not the problem.
Yeah, sounds good. I can give a little bit context, background information behind this. I'm very new, very, very new. I just got into this topic last fall, and I'm actually working as a material scientist and electrochemist. So Florin, he is our a program leader. So he mentioned the conversation, as you mentioned, people have doubt on whether those tracks are made by other factors, but not the energetic particles. So that's how I bring this idea into my design, and I redesigned the electrochemical cells to show that actually you can see that here we don't have any contact. This is complete in air. There's no contact. That's why I say, okay, I want to get it out from not only chemical, but also electrochemical, and also the electrical field. So that is how it's kind of complete, exclude those factors people may have doubt. Yeah.
Yep. Thank you. I will talk to this guy and explain it to talk to you. Thank you very much.
Okay, thank you.
Konrad Czerski.
You have mentioned in your presentation that you are looking for similar effects that Eric Ziem has measured some time ago. So, but the question is, you use this Mylar foil just for mechanical stability of the CR-39.
Yeah.
And his conclusion, however, was that he measured mostly helium-4, very, very low energy alpha particles, about 100 keV. The question is, could you measure that in your case? Because of the Mylar foils, it will be difficult, I think.
Right. You're definitely right, and it's a very good question too. So as I'm briefly mentioning in my talk, Mylar has different options for different thickness, and also in Palm's previous result, they didn't use any Mylar, and then they can catch more particles within wider range of the energy. So for us, it is only I use Mylar just because the limit when I designed this electrochemical cell, because I do need a mechanical force to help to put this very thin and soft gold layer. We have different options. I tried a 5 micron, 10 micron. So those are still we're still studying those different thickness of Mylar have different effect of the outcome of those tracks. But eventually, if we do not consider cost that much, we can directly just use gold, directly put on the CR-39 surface. But we also need to find a better way to produce thin layer gold, but strong enough. So yeah, it's not a perfect answer, but I want to let you know we're still working on that. And hopefully if you you want to follow up on that, then just feel free to contact me as well. Yeah.
I think that will be very difficult to determine mechanism of the reaction, if you measure this helium-4, low energy helium-4. And calibration, this is very important to calibrate the tracks at very low energies, which is really very difficult. You have so many sources for that,
Right. The calibration is very difficult. You're right. Yeah. So right now we only look at the relatively high energy particles. That's the limitation. Yeah.